homework 8, problem 1. Show that the following expression, which we call a standing wave, satisfies the wave equation, and then write this in terms of right and left moving waves. Well, first of all, let's write down what the wave equation is. The wave equation can be written 1 over v squared, the partial derivative with respect to t squared of some unknown function f of z and t, minus the second partial derivative with respect to z of f and z and t must equal 0. This is the wave equation. In order to show that it satisfies this, I will note, right, that the second derivative, so sine of x prime, the second derivative of sine with respect to x is minus sine of x, and same with cosine, so that whenever I take the derivatives here, I'm going to have to pull out the k because of the product rule. So if I take the derivative of sine of kz with respect to z, I have to pull out the k. If I take the derivative of cosine of kvt with respect to t, I have to pull out the kv. So if I take those derivatives twice, I have to pull out that constant k or kv twice, and then I'm going to get a minus sign. So writing that down, plugging this equation into that differential equation, I'm going to get minus k squared v squared over v squared, and then I'm just going to get f of z and t, and then minus, here I'm just going to, this is derivative with respect to z, so I'm going to pull out the k twice, k squared, but plus, so here's it minus, the minus there is going to give me a plus, and then f of z and t. Well, notice what I have here. I have a minus k squared f plus k squared f. This equals 0. So, therefore, it is proven. QED, quod erat demonstrat, so whatever the hell that is in Latin. Okay, now let's move on. Let's show that we can write the standing wave, which, here's a picture of the standing wave at 3 different times, right? I start out here, and then without the wave moving, it just gets smaller and changes amplitude, and it's going to wobble back up and down like this. A right moving wave, on the other hand, right, is going to look like that at time t1, but at time t2, it's going to look like that. And so it's going to appear to move in a rightward direction if I were to plot it like that. The way we can write this down is I can write f, and I'm going to put a subscript of either an r on top or an l on bottom for a right or left moving wave, of z and t is equal to amplitude, same amplitude, but now I'm just going to put a sine of kz minus or plus kvt. And that's simply an expression that I have a sine wave, and if it moves to the right, then I have, with a speed v, then I get minus vt. What is this called? Distribute the k to get that expression. If I'm moving to the left, then I have to add it, and so minus for right moving, plus for left moving. I can use a trig identity to rewrite this as a times quantity sine of kz cosine of kvt, ooh, that looks familiar, minus plus cosine of kz sine of kvt. And so now I note, or I just observe through observation, I can state that 1/2 of a right moving wave, z, t, plus a left moving wave, z, t, is going to equal our standing wave, f, z, and t. And it's just an observation that if I add the right to the left, I'm going to, the minus sign here is going to cancel with a plus sign, so the second term is going to go away. I get sine cosine, which is exactly what I have up here. I need the 1/2 to say that the amplitude of the left moving and right moving are half of the amplitude of the standing wave. And that's it.